Ever wish games could just work how you want them to work? Well, I reject any options to use pre-built engines to make my life easier. I'm just kidding, I just wanted to try something ambitious. Today, we'll talk about freeing the physics. This topic once again falls under the category of structuring. But rest assured, freeing the physics early prevents a lot of future problems, including potential multiplayer syncing. For those of you that don't know, physics refers to the logic that drives a game. The naive way of implementing this logic is by updating it in the main loop. Freeing the physics implies detaching the logic from the rendering. What's the point of having rendering and logic separate? Well, imagine Luncle and I play a game where the physics isn't freed, but he uses his beefy computer while I still use my handy-dandy retrogressive gaming toaster. If rendering and logic were dependent on one another, then Luncle's computer would be able to move a character much faster because his computer runs at 60 FPS while my computer runs at 5 FPS. So we want different quality computers to have the same gameplay. This is where freeing the physics comes in, so we can guarantee that the only difference between the two computers will merely be visual. Alright, so this is how we freed the physics in Nomads. Step 1. Put logic and visuals in different threads. They are now independent of one another, but a faster computer would still run the game faster. Step 2. Give the logic thread a timer for a fixed number of updates per second. This is done through introducing a target frame time variable, which defines how long the thread should wait before triggering another logic update. So now the quality of the computer does not matter at all, which is what we wanted. But it's also a waste of time because any render calls that happen between logic updates are useless. We want computers to expend their processing power on rendering. If a call happens between logic updates, ideally it should draw an in-between game state. So, step 3. Calculate interpolation with an accumulator. The accumulator is a variable that keeps track of how much time has passed since the last logic update. Divide that by the target frame time, and we get a percentage with which to interpolate by. Interpolating for constant speed entities should be like grade 9 math, so I won't go into too much detail about it. I'll give an example though of how we interpolated for variable speed, the camera. You may have seen in our last video how our camera smoothly followed the player. The math behind it is simple. Every frame, the camera simply approaches the player by 1/10 of the distance, i.e., take the vector that points from the camera to the player, scale it by 0.1, and add it to the original camera coordinates. But how do we achieve the same effect when the physics and rendering are separated? Every logic frame, we want the camera to be 1/10 closer to the player, and we want each rendering frame to be able to interpolate between two logic frames. A pretty cheeky way of figuring out math like this is to just graph the data. And once you do so, connect the dots, and it's pretty evident that the graph you plot is an exponential function with a base of 0.9. Given an alpha value, we simply raise 0.9 to the exponent alpha to get the correct scalar for the current rendering frame. Oh yeah, exponential interpolation. But Jary, how come you haven't run into your weekly issue yet? Ah, yes. Every week, a bug induces crippling depression upon us. If you'll recall, we've separated the logic from the visuals with the use of threads. With this comes many multi-threading problems that are unintuitive to solve. After freeing the physics, we encountered another problem. The character on screen twitches a bit as he moves. Yeah, that. God, it almost looks like he's possessed. Why does this happen? This was an oversight on my part. Previously, when rendering and logic updating were on the same thread, we simply loop through our entities list to update them, and then loop through them again to display. But this approach does not work when we have threads. This is because it takes time to loop through and update all the entities. So if the rendering thread requests data while the logic thread is not done updating everything, then we end up rendering a scene where some entities are updated while the others are one frame behind. No matter how fast we optimize the updating, we cannot avoid this problem. You can pause this video now if you want some time to think about how we solve this problem. The answer is buffers. Buffers, in concept, are temporary data storages for when you need to instantly swap out large amounts of data. This will be easier to understand if I give an example of a type of buffer you're probably already familiar with. That is, render buffers in computer graphics. If you've played around with any graphics libraries from basically anything, then you know that if you set your program to repeatedly refresh the screen and draw, say, a rectangle and a circle on top, you will never see an intermediate draw step, i.e. only a rectangle. How do they do this? This is done through having two canvases, where at any time, one is used for displaying, while one is used for drawing. When the computer is done drawing on one canvas, it switches the to-display canvas to the finished one. This is called double buffering. How does this apply to our situation? Well, using the same principle as rendering buffers, we simply duplicate the storage for every updatable variable, and at any time, we designate one copy of them to be the one used for displaying, while the other copy is used for updating. Every logic update, we tell the visuals to look in the completed buffer for display data and move on to do updates on the original one. And there we go, exorcism complete. Dear Diary, as a worthy paladin of the Holy Order, today was a glorious day. I freed the beautiful damsel named Physics from the castle, and also banished the demons possessing our bro Jary the Small. Triumphant I stand! I will fight with honor!